This lesson's on equivalent resistance. First, let's remember that resistance is defined as the ratio of potential difference across to current through a resistor, and also that when we have resistors in series, the current through the two resistors in series here is the same because there's nowhere else for the charges to go, and the potential difference across them adds. So if I were to measure the potential difference across this resistor and the potential difference across this resistor using a voltmeter across each, and then add those together, I'd get the same value from adding those as if I measured the potential difference across the two of them. Now, when I have resistors in parallel, like this, because there are branch points, there's two directions for the current to go. The current can go this way or the current can go this way. And so the current across the two of them adds. If I were to measure by putting an ammeter here, the current through this one and the current through this one, add those together, that would be the value I'd get if I put an ammeter over here. And now in this case, the potential difference across the two resistors in parallel is the same. So now we're going to use that information to work out what is called equivalent resistance. So first, what does equivalent resistance mean? Here's a circuit with two resistors in series, and what we're going to ask is, if we were to replace those two resistors, so take these two resistors out and replace them with one resistor, what resistor would we need to put there? We'll call that the equivalent resistor. What resistor would we need to put there so that we would draw the same current out from the cell as in this first case? So imagine replacing these two with one, and what would we need to put here so that from the perspective of the cell, it would look exactly the same? So if we think about the potential difference across the cell, in other words, if I were to put a voltmeter here across the cell, that potential difference has to be the same as the potential difference across these two resistors down here. And you can see that because the only difference between connecting down here and connecting up here is these wires. And if we assume that the wires have zero resistance, then there's no difference. Another way of seeing that is I could put the voltmeter here in the middle, and that's like the first case and like the second case. So connecting the voltmeter in these two places should be the same. So the potential difference across the cell has to be equal to the potential difference across 1 and 2. And we know by what we've seen for resistors in series that the two of them add. So if this is 1 and this is 2, the potential difference across 1 and the potential difference across 2 add because they are in series. So V cell must be equal to V1 plus V2. We also know from our relationship, our definition of resistance, that by rearranging R is equal to V over I, we can get V cell is equal to the total current out of the cell. In other words, if I put an ammeter there, what's that total current? Multiplied by the equivalent resistance. Now, why multiplied by the equivalent resistance? Because remember, what I'm trying to do is find an equivalent resistor such that from the perspective of the cell doesn't know, can't tell the difference between this situation and this situation. So the current passing out of the cell is the same in this case and in this case. And if I put a voltmeter down here, I'm going to get the same reading as the voltmeter over here. And that's the same reading as the voltmeter across the cell. So V cell has to be equal to the current out of the cell times the equivalent resistance because of this relationship and because of how I'm setting up the equivalent resistance. Now that's equal to the voltage drop at resistance 1, which is equal to the current through resistance 1 times its resistance. And then the same thing at resistor 2, the current multiplied by the resistance of resistor 2 in ohms. Now all three of these currents are the same because no matter where I put an ammeter, whether I put it here, whether I put it here, whether I put it here, I'm going to get the same reading because there's only one path for the current to go through. So I can factor out that current and cancel it because that's going to be all the same value. And so what I see, therefore, algebraically, is that the equivalent resistance in the series case is just equal to the sum of the two resistances. In other words, if this resistor is a 1 ohm resistor and this resistor is a 2 ohm resistor, then I would need a 3 ohm resistor to replace it as one resistor so that from the perspective of the cell, it would be drawing out exactly the same current. Let's say this is a 9 volt cell. In this case, if we have a 9 volt cell and a 3 ohm resistance, then because current is going to be equal to potential difference divided by our equivalent, this is V cell, this is my total current, then I get 9 volts divided by a total of 3 ohms is a 3 ampere current. And that would be the same in this situation or in this situation. Again, from the perspective of the cell, it can't tell the difference. Also notice that we've done this for just 2 resistors, but it would hold for 3, 4, and more resistors. And you can see that as you add more resistors, you would get a greater and greater equivalent resistance. So the cell would see a greater and greater overall resistance as you add more and more resistors in series. Now let's talk about resistors in parallel. Here's resistor 1 and here's resistor 2 in parallel. And remember that when we're talking about resistors in parallel, it's the current that adds. So if I were to put an ammeter here and get the current coming out of the cell, I'll call that I sub cell, that's going to be equal to I sub 1 and I sub 2. Because of this branching, those two have to add to the total current out of the cell. And again, what we're trying to do here is find an equivalent resistance so that if I were to replace all of this with one resistor like this, I'd still be drawing the same total current out from the cell here. So now, in this case, using the same relationship, we know that I cell is equal to V cell divided by the total resistance that it's seeing. In other words, the ammeter reading here is equal to the total potential difference across the cell divided by the equivalent resistance that it sees. That's going to be equal to, again, V1 over R1 plus V2 over R2. I'm just replacing each of these using the relationship, rearranging the relationship R is equal to V over I. Now in this case, because we know from our previous lessons that the potential difference across resistors in parallel is the same, and in this case that's going to be equal to the potential difference across the cell, now it's all of these potential differences that are the same. V cell is equal to V1 is equal to V2. So I'm just going to call that V, and I'm going to factor that out. And now if we cancel those, we can see that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. So for example, let's say this was a 1 ohm resistor, this was a 2 ohm resistor. Then to find the equivalent resistance, we would take 1 over 1 ohm plus 1 over 2 ohms. When you add that together, this becomes 2 over 2 plus 1 over 2. We get 3 over 2, but that's not our resistance. That's 1 over our equivalent resistance. And the common mistake that people make here is they forget to flip them upside down and give an answer that's incorrect of 1.5 ohms here. When you flip this upside down, the equivalent resistance is equal to 2/3 of an ohm, or let's call that 0.67 ohms. So notice here that as we've added more resistors, the equivalent resistance has gotten less. And in fact, it's lower than either of these two resistances. It's lower than 2 ohms, it's lower than 1 ohms, it's less than 1 ohm. And you can think of this as there being more outlets for the current to flow through. Just like if you have more doors out of a classroom, there's more ways for the students to exit, and that's easier. So adding more resistors in parallel will decrease the equivalent resistance. Now, you can have circuits where you have both of these happening. So let's say we had a circuit like this, where this is resistor 1, this is resistor 2, and this is resistor 3. The approach to working out the equivalent resistance would be to add these two, using the method we just described for resistors in parallel, turn those into one resistor that replaces both of them, and then combine that with the third resistor by adding them as you would for resistors in series. And by doing that, you can work your way up to the equivalent resistance for the whole circuit. So again, you're basically turning that into a circuit that looks like this. And then you can solve for things like the current out of the cell, because the current out of the cell in this situation, where this is the equivalent resistance, is the same as the current out of or into the cell over here. And so you can use this to solve for different unknowns in a circuit. So that's an introduction to equivalent resistance.